Hey guys, welcome back. Hopefully that you can hear me okay. I have tried so many different ways of getting this going. This is the best way that anyway, none of that matters. Okay, so let's pick up where we left off from last class. Again, this is chapter 9, and we're talking about atomic emission spectrum. All right, so what is that again? Well, let me just take you through a quick overview. So when an atom absorbs energy in the form of heat, light, or electricity, like it does in this neon sign, which is, so first of all, a neon sign is comprised of one or more tubes filled with neon gas, and they pass an electrical current through this gas. And then when they pass the electrical current, the neon atoms absorb this energy and re-emit it in the form of light. So atoms of different elements do the same thing. Light emitted from a mercury lamp, which is on the left, glows blue, while light from a hydrogen lamp appears red. So closer inspection of the light emitted from these elements show that each emission, or each glowing light, contains several different distinct wavelengths. Now, really fast, this is different than the white light spectrum that you would see from like the sun, where it is a white light, colors that are comprised of white light or that are within white light is a continuous spectrum. These emission spectrums are not continuous. They are comprised of distinct wavelengths. So the combination of these wavelengths present are characteristic of the elements that produce it. So if you see here, the hydrogen lamp spectrum, or excuse me, the hydrogen light spectrum only gives you 3 lines of red. It looks kind of like a green blue, and then there's a violet, while the helium gives you 1, 2, 3, 4, and then if you see a neon light spectrum, like it's completely different than the hydrogen or the helium. So this is really important because these emission spectra, all right, that spectra is the plural for spectrum, is identical to the element, all right? So this means that no two elements have the same pattern of wavelengths present, all right? And so we can actually use these spectra to identify elements because it's kind of like a fingerprint. So again, why is it that the hydrogen lamp glowed like a pink red, but then we end up getting these constituent wavelengths? So what do I mean by constituent? I mean constituent meaning part of a whole. Okay, so when we pass the pink red light concentrate it through a slit, and then pass it through a prism, the light refracts, okay, meaning it bends. And we already talked about, since red wavelengths bend the least amount and violet bends the most, you get a nice clear series of bright lines, and this is called the emission spectrum. Okay, so what does this mean? How does this help us understanding what an atom looks like, right? So the Danish physicist Niels Bohr attempted to develop a model that explained this atomic spectra that we see, these emission spectra. In his model, he said, okay, how about this? Electrons travel around the nucleus in these circular orbits, and these orbits exist only in fixed distances from the nucleus. Okay. The energy of these orbits are also fixed. They're quantized. All right. So just like steps on a ladder, Bohr orbits are at fixed distances from the nucleus. And the further away you are from the nucleus, the higher energy you have. This energy is specified by a quantum number, n. Just like when you climb a ladder and your feet cannot be in between 2 steps, electrons cannot exist between 2 orbits. They must exist within an orbit, and they possess the energy that is specific to that orbit. And this essentially is the Bohr model. So Bohr also proposed that electrons don't emit light, but by just existing on an energy level, okay? By just hanging out on their energy level. They have to be doing something. And it is only when an electron jumps or transitions between 2 energy levels that radiation right? Remember, electromagnetic radiation, that's another word for saying light, is either emitted or absorbed, okay? More specifically, radiation is absorbed when moving from a lower quantum number to a higher quantum number, so n equals 1 to like n equals 4. That's when radiation is absorbed. An electron has to absorb outside energy, right, to jump to a higher energy level. And radiation is released or emitted when electrons relax from a higher quantum number, let's say from like n equals 5, to a lower quantum number like n equals 1. So we go back to the hydrogen lamp example. We know that we pass a current through it, it glows red, pink. That pink light, again, is passed through a prism and yields 3 distinct lines, which is the hydrogen emission spectrum. These lines indicate 3 different relaxation pathways of electrons within the hydrogen atom. And we can rank them in order of energy, where red is the lowest energy transition, blue-green is intermediate, and violet is the highest energy transition. And again, we can do that because we know how wavelength and energy are related. We know that they're indirectly proportional. So red, 750, this one is 657 nanometer light, that has a lower energy than the violet at 434 nanometers. So remember, a photon is a packet of energy that has a wavelength associated with it. The energy of a photon is inversely proportional to its wavelength, and the light emitted by excited atoms consists of specific lines at specific wavelengths, each corresponding to a specific transition between 2 orbits. Okay, so what am I talking about now? So let's take apart this emission spectrum again of hydrogen and see exactly what we're talking about. So again, we know that hydrogen, when it's excited by electricity, the electrons jump from, we'll say, its ground state energy level, where all the electrons are probably around n equals 1, all right, on or within the n equals 1 orbit. When those electrons get excited, they jump up to higher energy levels. Now, they can't stay up there long, all right? It's not stable for excited electrons to stay in higher energy levels. They want to come back down. So in order for them to come back down, they have to release energy. They have to give away energy in order to relax back down to their to a lower energy state. So in order to do that, they must give off electrons. I'm sorry, they must give off photons. All right, so when the hydrogen atom relaxes back down, it emits photons with 3 different wavelengths. One, red, found at 657 nanometers. The other, blue-green, found at 486. And violet, 434 nanometers. Now, let's pick this apart. The red line at 657 nanometers, remember, that's the longest wavelength, meaning that's the lowest energy transition. So we can go ahead and correspond that to electron relaxing from the n equals 3 energy level, because remember, it was excited up to the n equals 3, and it relaxes down to the n equals 2 orbit. Likewise, we can look at this blue-green line at 486 nanometers. It's blue-green, 486 nanometers. That's higher energy. It's a shorter wavelength, so it's higher energy than the red photon at 657 nanometers. So we can go back and say, okay, well, that electron must be on the n equals 4 energy level, and it relaxes back down to the n equals 2. So overall, that's a change, a delta of 2 orbits. So it's a higher energy transition. And then finally, the violet line at 434 nanometers corresponds to relaxation, the highest energy relaxation, where we have an electron on the n equals 5 energy level, and it's relaxing back down again to the n equals 2. That's an overall change, delta n, right, of 5, 4, 3. That's 3 different energy levels that it relaxes back down. So hence, it is the highest energy relaxation of an electron of the hydrogen atom. And that is why we get these 3 different lines. Okay, so this was a really good attempt at creating or trying to understand the atom, specifically the electrons around the nucleus, but it wasn't totally correct, okay? It was just a first step in getting to where we're supposed to go. The great success of the Bohr model of the atom was that it correctly predicted the lines of the hydrogen emission spectrum. However, it failed to predict the emission spectra of many other elements that contained more than one electron. And so for this reason and other reasons, all right, the Bohr model was kind of replaced, or we'll say was a good the Bohr model was a good transition to a more sophisticated model called the quantum mechanical model or the wave mechanical model.